So this example, it says, this series circuit shown is similar to some radio tuning circuits. It's connected to a variable frequency AC source with a root mean square terminal voltage of 1 volt. These are the questions. A. Find the resonant frequency F0. B. At resonant frequency, find inductive reactance XL, the capacitive reactance XC, and the impedance Z. C. The RMS current, the IRMS. D. The RMS voltage across each circuit element. This is the stage you would go when you solve a problem like this. You identify and set up everything. The circuit diagram, right, so we draw the circuit diagram here, shows an LRC series circuit with ideal meters inserted to measure the RMS current and voltages, which are our target variables. Equation 3, which is this equation here, includes the formula for the resonant angular frequency, W0. We can find the resonant frequency F0 very easily. We use equations 1 and 2 to find the XL, so that part of the question, the XL and the XC. So we've got that. We've got these equations here. Those 2 points are equal at resonance from equation 7, so we can see that here. At resonance we have Z equals R, because those 2 bits go to 0, so we know that Z equals R then. We use equations 4, 5 and 6 to find the voltages, so finally we'd use that equation to find the voltage across the resistor, that one to find the voltage across the inductor, and that one to find the voltage across the capacitor, because we'll then have all those values. So we're going to do A now, find the resonant frequency F0. The value of W0 and F0 are W0 equals 1 over the root square LC, where we've got L and we've got C, they're given to us. So we just plug it into that equation and we get 5 times 10 to the 6 radians per second. Therefore, the resonant frequency F0 equals W0 over 2 pi. Remember, the 2 pi F equals W0, so now we can simply get the F0 by dividing the angular frequency by 2 pi. We get 8 times 10 to the 5 hertz, which is 800 kilohertz. This frequency is the lower part of the AM radio band, so this circuit then we now know is tuned to 800 kilohertz. At this frequency, XL equals WL. Now we've got the frequency, we can find the reactance that is produced by the inductor. That's 5 times 10 to the 6 times 0.4 times 10 to the minus 6. That's 2,000 ohms. So that's the reactance provided by the inductor. And the reactance for the XC is 1 over WC. So we plug those and we find that that's 2,000 ohms. So look, they're both the same reactance. Since XL equals XC at resonance, as stated above, this part of the equation now that goes to 0, and we're just left with the R. Z equals R, which is 500 ohms, which is given to us. Now for C, from equation 8, which is here, the RMS current at resonance is, we just rearrange that equation there, and we get VRMS over Z. So we've got VRMS is 1 volt, we was given that at the beginning, that's 1 volt, divided by 500 ohms, so then we've got the RMS current is 2 milliamps. So that's the root mean squared current. Finally, for D, the question was the RMS voltage across each circuit element. So now we've got all the values, we just plug these in. We've got the RMS, which was 2 milliamps, times the R 500. So the voltage across the resistor is 1 volt. Plug in all the values for the inductor. We'll find the voltage across the inductor is 4 volts. And the voltage across the capacitor is 4 volts. Well, we knew they'd be 4 volts because they're going to cancel. So when you drop the, remember, one is going to be minus and one is going to be plus at all times. That's why when you drop a meter across there, the voltage is always going to be 0. So just evaluating the results a little bit more, the potential difference across the inductor and the capacitor have equal RMS values and amplitudes, but are 180 degrees out of phase, and so they add 0 at each instant. Note also that at resonance, the voltage across the resistor is equal to the source voltage, VRMS, while in this example, root mean square voltage across the inductor and the voltage across the capacitor are both considerably larger than the volt root mean square. Follow-up question, how does the resonant frequency of an LRC series circuit change if the plates of the capacitor are brought closer together? Well, that's easy. You can just go to this formula here. You know, if C gets big, 1 over a larger number is going to give you a smaller number, so you can see that the resonant frequency is going to decrease. That's the follow-up question. And that's a really good example of resonance in an LRC circuit.